Okay, so let's look at some examples. Given the probability distribution, find the following values. So this is a probability distribution. You can see I'm saying x, that's my random variable, and I have values of 1, 5, 10, and 20. Those are the possible values that x can take on, and I've given their associated probabilities down here, 7/15ths, 2/15ths, 1/5, and 1/5. So those are the values of my random variable and the associated probabilities. This is why I'm calling this a probability distribution. To find out the probability that x equals 1, that's what this is saying, the probability that x equals 1, well, this is just 7/15ths. Don't be alarmed by having an equal sign inside your parentheses. That's just saying the probability that this particular event has happened. You can do things like the probability that x is greater than or equal to 10. So that would be, well, 10 and 20. Well, this would be 1/5 plus 1/5, which is 2/5. So the probability that x is greater than or equal to 10 is 2/5. Now, this particular example, you might look at this and say, okay, well, this seems like kind of a weird example. Where in the world would something like this happen? Well, how I came up with this example, let me write these as not reduced fractions. This would be 3/15ths, and that would be 3/15ths. If you have 15 bills in your wallet, 7 of them are $1 bills, 2 of them are $5 bills, 3 of them are $10 bills, and 3 of them are $20 bills, and you pick one at random, the probability that that is a $1 bill is 7 out of 15. You can see that's exactly that number there. The probability that the bill has a value of greater than or equal to $10 is going to be 2/5. That's those two probabilities added up right there. Now, the expected value, this is if you were to take your wallet and pick a bill out and repeat this experiment several different times, which means you would have to be putting the bills back between each time sampling, and average together those values, that's what this expected value would end up being. To actually compute it, what I'm going to do is I'm going to go through and say, okay, for this is my first outcome. It has a probability, or a value, my random variable is 1, and it has a probability of 7/15ths. So I'm going to do 1 times 7/15ths. Then I'm going to do 5, so now I'm looking at the second outcome here. 5 times 2/15ths plus 10 times 3/15ths. Oops. 10 times 3/15ths plus 20 times 3/15ths. Now if I add all these together, this will give me the expected value for a bill in this wallet. Alright, so I'm going to I kind of intentionally kept all these with a denominator of 15 because I wanted this to have a denominator of 15 at the very end, so I can kind of ignore them in the middle of the problem and just deal with my numerators. So 1 times 7 is 7, 5 times 2 is 10, 10 times 3 is 30, and 20 times 3 is 60. So this would be 107/15ths. 107 divided by 15, which is 7.13 repeating. So the expected value, if I reach into my wallet and I draw a bill out, my expected value is 7.13 repeating. Do not let the fact that there is no $7.13 bill in your wallet be that's not a problem here, because this is, like I said, this is an average. It is the expected value. So it's kind of the middle. It's the middle of the road. You can see it's middle of the road, except it's balanced by how big these bills are. So these are $20 bills, so they actually have more pull than the $1 bills, but there's more $1 bills in there, so that kind of allows them to have more pull. That's kind of why they balance each other out here. All right, let's draw a histogram and think about how this relates to what happens with the histogram. So let's see, in this histogram, this is just a bar chart, so I'm going to go 1, 2, 3, 4, 5, 6, 7, go like this. This is 1, 5, 10, and 20. These are all the different outcomes. I have a probability of 7 out of 15 up here. I have the probability of 2 out of 15 here, 3 out of 15 there, and 3 out of 15 there. So if I was to draw my histogram, it would look something like this. This is just a bar chart. of all the different outcomes and their associated probabilities. That's what my histogram looks like here. Now, an interesting thing about this expected value, how it relates to the histogram, if I was to draw this so that the scale actually matched up, so maybe I should actually do a slightly different version here. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I'm running out of room. Let's make these steps of 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. If I was to actually make this so it was to scale and draw my histogram this way, so I would have a $1 bill occurring 7 out of the 15 times, a $5 bill, 5 is in here, occurring 2 out of the 15 times, and a $10 bill occurring 3 out of the 15, and a $20 bill occurring 3 out of the 15. Then this expected value would actually be a center of mass. So, you know, if these were actually masses on here, and 7 is approximately 7.13 is approximately right there. This would actually be the center of mass here. So you can see this is more heavily over here. The $1 bills are more frequent, and so that makes that appear a little bit heavier. But also this is farther out, so that kind of counterbalances the fact that the $1 bills are heavier. So that's why I was talking about that whole. Well, yeah, this is center of mass. If I was to set this up, it would balance right on that point.